Hello. Today I'm going to work through a set of questions that you might typically get in an A2 level physics exam on quantum, nuclear and particle issues. First, let's just talk through the formulae you're likely to need. E equals hf, which means that the energy is equal to Planck's constant times the frequency. That is sometimes written h nu, where nu is also the frequency, and that is also equal to hc over lambda, where c is the speed of light and lambda is the wavelength. 1 electron volt is what you get when one electron is accelerated through 1 volt. It's a measure of energy, and it is equivalent to 1.6 times 10 to the minus 19 joules, because of course an electron carries a charge of 1.6 times 10 to the minus 19 coulombs. So if you use the formula that energy is equal to the charge times the voltage, that's where that comes from. It also is a means by which you can convert from electron volts to joules. You multiply by 1.6 times 10 to the minus 19. Or if you're coming the other way, if you want to convert from joules to electron volts, then you have to multiply by 1 over 1.6 times 10 to the minus 19. Kinetic energy we know is half mv squared. Then we get to the Debroglie equation. Lambda equals h over p. Lambda is the wavelength of either a photon or an electron. H is Planck's constant and p is momentum. If you're talking about electrons, then that can be written as h over mv, where m is the mass of the electron and v is the velocity. You can't write that for photons, of course, because photons don't have mass. When you're talking about the radius of a nuclei, the radius of a nucleus is equal to r0 times a to the 1/3, where a is the number of nucleons in the nucleus. Then I've just reminded you of Coulomb's law. Force is equal to, this is the force between two charges, is equal to Q1, Q2, the charge on the two particles, divided by 4 pi epsilon naught r squared. Epsilon naught is the permittivity, usually of free space, and r is the distance between the two particles. Einstein's famous formula E equals mc squared. Then you've got the decay formula, A equals lambda times n, where A is the amount of activity, the number of decays, lambda is the decay constant, and n is the number of atoms. Then n equals n0 times e to the minus lambda t. N is the number of atoms remaining after a certain time t. N0 is what you started with. Lambda is the decay constant. And finally, the half-life is given by log to the base e of 2 divided by the decay constant lambda. Question 1. We have some kind of metal on which we shine light with a wavelength of 5.5 times 10 to the minus 7 meters, and we find that we get electrons emitted with a maximum kinetic energy of 2.2 times 10 to the minus 19 joules. And we're asked to find two things. Firstly, what is the wave function of the metal? And secondly, what is the maximum wavelength which would still enable you to release electrons? Well, first we need to identify the energy of the incident photons, and energy is equal to hf, or h nu, which is equal to hc over lambda, and that's going to be equal to, let's put it down here because it's going to be quite long, Planck's constant, which is 6.6 times 10 to the minus 34, times the speed of light, which is 3 times 10 to the 8th, divided by the wavelength of the incident radiation, which was 5.5 times 10 to the minus 7. And that, going through a calculator, will come to 3.6 times 10 to the minus 19 joules. That is the energy of the photons. That energy is used to kick the electrons out of the atom. In order to do so, it must overcome the binding energy, or the work function, and any energy that is left over will be coming out as kinetic energy, and the maximum kinetic energy is 2.2 times 10 to the minus 19 joules. So consequently, the work function must be the difference between the energy of the photon and the energy, the kinetic energy of the electron. So that's going to be, in other words, the phi, the work function, or the binding energy, is going to be 3.6 times 10 to the minus 19, which is this value, the value of the incident, the energy of the incident photon, minus the energy of the kinetic energy of the particles, the electrons, when they come out, which is 2.2 times 10 to the minus 19. And that is going to be 1.4 times 10 to the minus 19 joules. So the work function was 1.4 times 10 to the minus 19 joules. The photon had to give that much energy in order just to get the electron out, and any surplus energy comes out as kinetic energy. Now we're asked, what is the maximum wavelength that would still get an electron out of that metal? Well, again, we're going to use the formula that E equals hc over lambda, and we can rewrite that as lambda equals hc over E, and that's going to be, and lambda of course is what we want, and that's going to be h, which is 6.6 times 10 to the minus 34, times c, which is 3 times 10 to the 8th, divided by the energy to get the electron out of the atom, and we just calculated that. That was 1.4 times 10 to the minus 19, and that will give a wavelength of 14.1 times 10 to the minus 7 meters. Question 2. We have a cathode and an anode. The anode is the positive side of the diagram, and the anode is made of a material whose work function is 1.8 electron volts. We shine light onto that metal, and the wavelength is 5 times 10 to the minus 7 meters. And the question is, what voltage do we need to put across that arrangement in order to stop the electrons from emerging from the anode? Well, remember that electrons would normally, of course, emerge from the cathode. That's the whole point. They don't normally come from an anode, but if you shine light on them, then the photoelectric effect would take place, and the electrons will emerge with kinetic energy. If we put a certain voltage on this whole arrangement here, we will effectively suppress the release of those electrons. And the question is, what voltage do you need to do that? Well, let's take it a bit at a time. The energy of the incident photon is going to be hf, which is hc over lambda, just as we've shown before, and that is equal to 6.6 times 10 to the minus 34, that's h, times c, 3 times 10 to the 8, divided by the wavelength, which was 5 times 10 to the minus 7 meters, and that is going to give you 3.96 times 10 to the minus 19 joules. Now, since we've got a work function in electron volts, we better convert the energy here into electron volts. And the way to convert a joule into an electron volt, remember, was to divide by 1.6 times 10 to the minus 19. So if you divide this number by 1.6 times 10 to the minus 19, that will give you 2.475 electron volts. Now we know that phi is 1.8 electron volts, and the energy of the incident photon is 2.475 electron volts, and that would mean that electrons would emerge with a kinetic energy of 2.475 minus 1.8, which is 0.675 electron volts. And energy is defined as, energy in electron volts is the energy that one electron gets when it is accelerated through a voltage of 1 volt. So a kinetic energy of 0.675 electron volts is the energy that an electron would get if it was accelerated through 0.675 volts. Consequently, if you put 0.675 volts across in this way, such that this is the positive terminal In other words, it's trying to stop the electrons from emerging because they are negatively charged, and this is now going to be positively charged. If you put 0.675 volts across, so the PD is equal to 0.675 volts, you'll stop the electron from emerging in the first place. Question 3. We have two metal plates across which we've placed a voltage of 400 volts. We have an electron in the electric field, and the question we're asked is, what is the velocity of that electron and what is the wavelength of that electron? Well, we know that the definition of an electron volt is that that is one electron being accelerated through 1 volt. So the energy of this electron is going to be equal to 1 electron being accelerated through 400 volts. So it's simply going to be 400 eV. But we need to convert that to joules. So that's going to be 400 times 1.6 times 10 to the minus 19 joules. And that equals 640 times 10 to the minus 19 joules. Energy, of course, is half mv squared. That's the kinetic energy. And so consequently, that leads to v squared equals 2e divided by m. So v squared is going to be 2 times the energy, which we just identified, 640 times 10 to the minus 19, divided by the mass of an electron, which you would be given 9.1 times 10 to the minus 31. And that comes to 140.6 times 10 to the 12 meters. Well, actually it's v squared. So now we need to take the square root of that value, and that comes to 11.9 times 10 to the 6 meters per second. Part 2 asks us to find the wavelength of those electrons, and for this we need the Debroglie formula, lambda equals h over p, which, because we're talking about electrons, we can say that momentum p is equal to mv, and that is going to be equal to h, which is 6.6 times 10 to the minus 34, divided by the mass of an electron. Again, you'll be given that 9.1 times 10 to the minus 31, times the velocity, which we just calculated, which is 11.9 times 10 to the 6 meters per second. And if you put that into your calculator, you should get that that comes to 6.09 times 10 to the minus 11 meters. That's the wavelength of the electron. Question 4. Cesium has two energy levels which are separated by 3.8 times 10 to the minus 5 eV. They happen to be the energy levels that are used for cesium clocks. The question is, what is the frequency of the radiation that will cause an electron to jump from one level to the other? Again, we need E equals HF, and that gives us that F is equal to E divided by H. We know that the energy is 3.8 times 10 to the minus 5 electron volts, so we've got to change that to joules to get in SI units. So the frequency is going to be E, which is 3.8 times 10 to the minus 5 electron volts, but now multiplied by 1.6 times 10 to the minus 19, now in joules, divided by Planck's constant H, which is 6.6 times 10 to the minus 34. And if you do that with your calculator, you should get that that is 9.2 times 10 to the 9 hertz. Question 5. An atom has 12 nucleons and its nuclear radius is 3.2 times 10 to the minus 15 meters. What is R0? Well, here we're going to use the formula that Rn, the radius of a nucleus, is equal to R0 times the cube root of A, where A is the number of nucleons, and that simply means that R0 is equal to Rn divided by the cube root of A. So R0, which is what we want, is Rn. We were told that that is 3.2 times 10 to the minus 15 meters. And that's going to be divided by A, which was 12, so it's the cube root of 12. And if you put that into your calculator, you should get that that is 1.4 times 10 to the minus 15 meters. Part 2, what is the radius of an atom that has 218 nucleons? Well, here we just need to go back to this formula and say that Rn is equal to R0, which we've just calculated, 1.4 times 10 to the minus 15, times the cube root of, that should be the cube root of 218. And again, if you put that in your calculator, you should get, since the cube root of 218 is 6.018, that will give you 8.42 or 8.43 times 10 to the minus 15 meters. Question 6. Gold has a density of 19300 kilograms per cubic meter. But a gold nucleus has a density of 1.47 times 10 to the 17 kilograms per cubic meter. What does that tell you about a gold atom? Well, all the mass of an atom pretty much is in the nucleus. The electrons account for very little. And so you can say that the density of an atom is equal to the mass of an atom divided by the volume of an atom. You can also say that the density of a nucleus is equal to the mass of the nucleus divided by the volume of the nucleus. But the mass of the nucleus is equal to the mass of the atom because all of the mass of the atom is in the nucleus. So these two values are the same. So we can now say that the density of an atom times the volume of an atom is equal to the density of the nucleus times the volume of the nucleus. And if we now say that dividing rho by rho, you get rho of an atom divided by rho of the nucleus is equal to the volume of the nucleus divided by the volume of the atom. All right, I've just taken, this is rho incidentally in case you think it's this. So if you divide both sides by rho nucleus, you get rho of the atom divided by rho nucleus. If you divide both sides by the atom, you get volume of the nucleus divided by volume of the atom. And we were given these values up here. We've got, that's the rho for the atom, that's rho for the nucleus. So if we now put rho for the atom, that was 19300 kilograms per meter cubed divided by rho for the nucleus, which is 1.47 times 10 to the minus 7, sorry, 10 to the plus 17. You can see that this number is vastly smaller than this number. So the volume of a nucleus is vastly smaller than the volume of an atom. Consequently, most of the atom is pure emptiness, and only a very small part of it constitutes the nucleus. Question 7. Two protons are separated by a distance of 10 to the minus 14 meters. What is the Coulomb force between them? Well, this really is a question for the electricity side, but the Coulomb force is Q1, Q2 divided by 4 pi epsilon naught r squared. You'll almost certainly be given the value of epsilon naught, so that will become Q1, Q2, well, it's two protons. Each of them will have the same charge as an electron, so that's 1.6 times 10 to the minus 19, but it's squared because it's Q1 times Q2, divided by 4 pi times epsilon naught, which is 8.85 times 10 to the minus 12, as I say, you'll normally be given that, times the separation, which we were told was 10 to the minus 14, and that of course is also squared, And the most difficult thing here now is to keep track of all the 10 to the minuses, and that comes to 2.3 newtons. So that's the force between two protons, and of course it will be a repulsive force because they are like charges, so they're going to repel. Question 8. Radon has 226 nucleons and 88 protons. It decays into radon and an alpha particle. What is the equation? Well, we start by writing down, which we were told has 226 nucleons, that goes up there, and 88 protons. Proton number goes at the bottom left-hand corner, nucleon number top left-hand corner, and that is going to decay into radon. This is radium, this is radon plus an alpha particle. Well, an alpha particle, you should know, is 2 protons and 2 neutrons, so the nucleon number is going to be 4 and the proton number is going to be 2, and you know that the nucleon number must be conserved and the charge number must be conserved, so the total number of nucleons must be the same. If this is 226, then this must be 222, so that 222 plus 4 equals 226. The charge numbers must be conserved. We have 88 here, so we must have 86 here, so that 86 plus 2 equals 88. Question 9, which has 40 nucleons and 19 protons, decays to calcium by beta decay. What is the equation? Well, again, we were given that potassium has 40 nucleons and 19 protons, and we are told that it decays to calcium plus a beta particle. Beta particle is of course an electron, which means it will have no nucleons because it's a lepton, and its charge will be -1. And so now all we've got to do is to conserve the nucleon number at the top and the charge number at the bottom. To do that, we need 40 here because 40 equals 40 plus 0. And here we need 20 because 19 equals 20 minus 1. Question 10. We're told that the mass of an alpha particle is 6.425 times 10 to the minus 27 kilograms. We're told that the mass of 2 protons and 2 neutrons is 6.693 times 10 to the minus 27 kilograms. And so we're asked, what is the energy that is obtained from the production of an alpha particle? Well, an alpha particle, of course, consists of 2 protons and 2 neutrons, but bound together in an alpha particle. And so we will say that the difference between these two masses, the mass of just 2 protons and 2 neutrons, and the mass of an alpha particle, is what's called the mass deficit. And you can convert that into energy by Einstein's formula, E equals mc squared, where m is the mass deficit. So now we're going to say that the energy that's released when an alpha particle is formed is going to be the mass deficit, which is this number minus this number. I think you'll find that will be 0.268 times 10 to the minus 27 times c squared, which is 3 times 10 to the 8 squared. And that comes out to an energy of 2.412 times 10 to the minus 11 joules. Question 11. We have a radioactive source which is decaying. It has 100,000 atoms originally. We're now doing a measurement and we find that the decay rate is 800 becquerels. The background decay rate is 40 becquerels. And we're asked, what is the decay constant? What is the half-life of the radioactive material? And how many atoms will be left after 10 minutes? Well, a becquerel is 1 decay per second, so 800 becquerels is 800 decays per second. But if we're measuring 800, we must remember that 40 of those are natural background radiation. So the actual decay from this source is just going to be 760 becquerels, or 760 decays per second. And we're going to use the formula that A, the activity, is equal to lambda, the decay constant, times n, the number of atoms. And we are told that A is 760, well, it's 800 minus 40. And that's going to equal lambda, the decay rate, which is what we need to find, times n, which is 100,000. And if you do the sums, you'll simply see that lambda is 760 divided by 100,000, and that equals 0.000076 per second. Oh, sorry. Let's do that again. Lambda is going to be 760 but divided by 100,000, which is 0.0076 decays per second. So that's lambda. Now we need to find the half-life. So we're going to use the formula that the half-life is equal to log to the base e of 2 divided by lambda. Log to the base e of 2 is 0.693. And lambda we've just calculated is 0.0076, and that is going to give you a half-life of 91.2 seconds. And then how many atoms will be left after 10 minutes? Well, for that we need the formula that the number of atoms is equal to the original number of atoms times e to the minus lambda t. And that means that n is going to be equal to the original number, which was 100,000, times e to the minus lambda, which is 0.0076, we calculated that, times t, well, 10 minutes is of course 600 seconds, which I hope comes to 1046. And to give yourself an idea of whether that is reasonable or not, remember, it halves every about 90 seconds. So how many 90 seconds are there in 10 minutes? Well, that's about 6.5. So if you think there were 100,000 originally, after the first half-life there will be 50,000, after the second there will be 25,000, after the third there will be 12,500, after the fourth there will be about 6,000, after the fifth there will be about 3,000, after the sixth there will be about 1,500, and after the seventh there'll be 750. So it's somewhere between 1,500 and 750. So that's probably about right. Question 12. We're told that the mass of a carbon atom, which has 14 nucleons and 6 protons, is 13.999948 atomic mass units. And one atomic mass unit is equivalent to 1.66 times 10 to the minus 27 kilograms. We're told that a proton has a mass of 1.007276 units, and we're told that the mass of a neutron is 1.008665 units. And the first question is, what is the mass deficit of the carbon atom? Well, we know that a carbon atom has 6 protons. If it has 14 nucleons, it must have, by definition, 8 neutrons. So you would expect that the carbon atom, you would expect it to have 6 lots of proton masses, which is 6 times 1.007276, plus 8 lots of neutron masses, which is 1.008665, and that comes to 14.112976 atomic mass units. But we are told what the actual mass of the carbon atom is in mass units, and so the difference, the mass deficit, is the difference between what you would expect it to be and what it actually is, and that if you subtract one from the other, you find that the deficit is equal to 0.1876 times 10 to the minus 27 kilograms. That's by calculating the difference and then multiplying by the value of the unit in kilograms. Part 2 of the question, what is the binding energy of that carbon atom? Well, the binding energy must be the energy equivalent of the mass deficit, because we've given up that mass, we've given up that energy, that is therefore the binding energy. And that is going to be determined by using Einstein's formula that E equals mc squared. So E is going to be the mass deficit, which we just calculated as 0.1876 times 10 to the minus 27 kilograms times c squared, which is going to be 3 times 10 to the 8 squared, and that's going to be in joules. And that, if you multiply that all out, you should get 1.688 times 10 to the minus 11 joules. And if we want the binding energy in electron volts, which quite often is the case, then you're going to have to convert joules to electron volts, which we do by dividing. So 1.688 times 10 to the minus 11 divided by 1.6 times 10 to the minus 19 will give you the energy in electron volts. And that is going to come to 105.5 MeV, or 105.5 times 10 to the 6th eV. Question 13, part 1. Here is a formula for the decay of iodine into xenon, plus an electron, plus an antineutrino. It isn't complete. We're asked to complete the numbers that should be associated with each of these particles or atoms. Well, the way to start is to say that we know what these should be. An electron, of course, has no nucleons because it's a lepton, and it'll have a charge of -1. A neutrino and an antineutrino have neither nucleon numbers, nor do they have a charge. And so now all we have to do is to balance the equation. We've got 131 on each side, so that's okay. And now we've got 53 has got to be equal to 54 minus 1. And so the correct value for xenon is 54. Xenon has 54 protons. The second equation we have to do is we've got radon decaying to polonium plus an alpha particle. And you can see unhelpfully they haven't given us any numbers at all here, but we do know that radon has 219 nucleons and 86 protons. So how are we going to find out what that is? Well, we should know that an alpha particle comprises 2 protons, 2 neutrons, so its total nucleon number is 4, and its total proton number or charge number is 2. And now we just have to make the equations balance. So this has to be 215, because 215 plus 4 must equal 219. And similarly, on this side, we must have 84, because 84 plus 2 must make 86. Question 14. The kinetic energy required for 2 protons to fuse is 1.1 times 10 to the minus 13 joules. What temperature do you need to achieve that, given that Boltzmann's constant is 1.38 times 10 to the minus 23 joules per Kelvin? The formula we need here is the thermodynamic formula, E equals kT, where K is Boltzmann's constant, T is the temperature, and E is the energy. And we have been told that we need an energy of 1.1 times 10 to the minus 13 joules. So consequently, we've got that the temperature is equal to E divided by K, and that's going to be the energy we need, 1.1 times 10 to the minus 13 joules, divided by Boltzmann's constant, which is 1.38 times 10 to the minus 23. And if you calculate that out, you should get that that comes to 7.97 times 10 to the 9 Kelvin, or 7 billion degrees. This is an equation, this is question 15, this is an equation for a deuterium-tritium reaction, and it's the sort of thing that would go on in a fusion reactor. We've got deuterium plus tritium produces an alpha particle plus a neutron plus energy. And we're given values for the mass units of these different elements. The deuterium, 2.013553 atomic mass units. Tritium, 3.015501 atomic mass units. Alpha particle, 4.001505 atomic mass units. And a neutron has 1.008665 atomic mass units. And we're asked to find the mass deficit and the energy released. And we're given the helpful information that 1 atomic mass unit is equivalent to 931 MeV. And the way to do this obviously is to add together the atomic mass units for the deuterium and the tritium, and then add together the atomic mass units for the alpha and the neutron, and to subtract one from the other, and that gives you the mass deficit. And if you do that, you should get that the deficit is equal to 0.018884 atomic mass units. And if we want to know what that is in terms of energy, then we have to multiply that by 931 to get it in MeV, and that comes to 17.6 MeV. So every time this reaction happens in a fusion reactor, you get 17.6 MeV of energy released. Question 16. Here are 5 reactions. Which ones are possible and which ones are not? The thing we have to remember is that the baryon number, that's proton, neutron, is to be conserved. That the lepton number, that's electron or neutrino number, must be conserved. And for each of the electron types and neutrino types separately, which means that it's either electron or muon or tau, but they can't be mixed, and that charge must be conserved. So let's have a look at each one and see if they're okay. Firstly, a neutron decays to a proton, an electron, and an anti-electron neutrino. Well, baryons are okay because we've got one baryon on one side and one baryon on the other. Leptons are okay because we've got a electron lepton and an anti-electron neutrino, so that's effectively +1 for the lepton here and -1 here, and nothing on this side, so that's okay. And charge is okay because you've got no charge on this side and you've got a plus and a minus on this side, and of course the neutrino has no charge, so that is okay. Next we've got a proton decaying into a neutron, an electron and an electron neutrino. Well, the baryon numbers are okay. We've got a baryon number of 1 here and 1 here, so that's all right. Lepton numbers are not okay because we've got a +1 lepton here and +1 lepton here, but no leptons on that side. So one of these should be an anti. Either you need a positron here or you need an anti-neutrino here. And then as far as charge is concerned, well, we've got a plus charge on this side and we've got a minus charge on this side. So again, even charge won't work. So that's not going to work. Here we've got a proton and a proton becoming a proton and a kaon. Well, that's not going to work because we've got 2 baryons on this side, but only 1 baryon on this side. A kaon is a meson, and a meson is not a baryon. So that's not going to work. Then we have a pion becoming a muon plus an anti-mu neutrino. Well, that's okay because a pion is a meson, but on this side we've got a muon and effectively an anti-mu neutrino. So the mu values are +1 and -1, so that's all right. And then finally we've got a mu neutrino plus a muon becomes an electron and an electron neutrino. Well, on the left hand side we've got a muon and a mu neutrino, so the lepton numbers on this side are +2. On this side you haven't got muons, you've got electrons and electron neutrinos, but leptons must be balanced by their qualitative parts. So muons must balance and electrons must balance, and they don't. So that's not permitted either. Question 17. We have a cyclotron which has a magnetic field of 40 milliteslas, and that is going to accelerate protons. We're given that the charge on a proton, which of course is the same as a charge on an electron, is 1.6 times 10 to the minus 19 coulombs, and that the mass of a proton is 1.67 times 10 to the minus 27 kilograms. And what we're asked is, what is the frequency required for the cyclotron? We start with the formula that we derived in electromagnetism, that the force on a charged particle in a magnetic field is BQV, where B is the magnetic field, Q is the charge on the particle, and V is its velocity, and that essentially is the force which provides the centripetal force to get that particle to go round in a circle, which is what it does in a cyclotron. And if you rearrange this formula, you get that V is equal to BQR over M, where M of course is the mass of the particle, R is the radius of the circle. And now we can say that the period, the time it takes for one complete cycle, is going to be the distance travelled divided by the velocity. The distance travelled is simply going to be 2 pi r, where r is the radius of the circle, and the velocity we've just calculated is bqr over m, so that's bqr over m. The r's cancel, and now you get that the period is 2 pi m over bq. But the frequency is of course 1 over the period, so the frequency is going to be bq divided by 2 pi m. And now it's just a case of putting in the values. Well, B we were told was 40 milliteslas, so that's 40 times 10 to the minus 3. The charge on a proton is 1.6 times 10 to the minus 19 coulombs, divided by 2 pi times the mass of the proton, which is 1.67 times 10 to the minus 27 kilograms. And again, if you put that into your calculator, you should get that that comes out at 6.1 times 10 to the 5 hertz, or if you prefer, that is also equal to 0.61 megahertz. And finally, 3 questions where we're asked to draw Fineman diagrams. The first is question 18. Draw the Fineman diagram which represents the electromagnetic repulsion of 2 protons. Always remember with Fineman diagrams, time goes upwards. So in other words, the progress is always up. So we've got 2 protons, a proton and a proton, and there must be some kind of interaction between them. And of course that interaction is photon exchange, and then the protons go off on their merry way. They don't change, they are simply repelled. And what is actually happening is that the force is exerted by virtue of the exchange of virtual photons, and that force represents the change of momentum of the photons as they are firstly emitted and then absorbed. Question 19. Draw a Fineman diagram which represents the interaction of an anti-electron neutrino with a proton. So once again we have the particles coming in from the bottom. Traditionally you put the baryon number, or the baryon, the proton, on the left hand side and the lepton on the right hand side. In this case it's an anti-electron neutrino, and what you're going to get here is an interaction, a neutron coming out here, and a positron coming out here, and a W plus conveying charge away. Now what we've got to check is to make sure that charge is okay. So we've got a positive charge coming in. The neutron has no charge, but the positron has a positive charge. And of course the incoming neutrino or antineutrino had no charge, so charge is okay. Leptons are okay. We've got a lepton coming in and an electron coming out, and they're both electron types. And baryons are okay because we've got a proton coming in and a neutron going out. And that is achieved by the weak interaction, hence the W plus. It's the W plus because it's conveying away a positive charge. Of course, you could have exactly the same interaction, but with a W minus going across in the opposite direction. And finally, question 20, we're asked to describe what goes on in the Sun where a proton is converted into a neutron. So here the only incoming particle, of course, is the proton. And the outgoing particle, so that's the incoming particle, the outgoing particle must be the neutron. There is obviously going to be some kind of exchange, and we're going to have some particles coming out. Well, obviously what we've got to convey away is the positive charge, because a proton has a positive charge, a neutron doesn't. So the positive charge has to be conveyed away. That's by a W plus. And that's got to be given to a positron. And then to balance the fact that you need to balance the lepton numbers, we're going to need an anti-electron neutrino. So now we've got baryon numbers conserved, proton in, neutron out, that's okay. No leptons come in, but an electron, a positron goes out. Oops, there's a mistake there, of course, it's not an anti-electron neutrino, it's just an electron neutrino, because this is a positron, so that's an anti-electron, so you now need a ordinary neutrino to balance it. So now we've got leptons +1 for the neutrino, -1 for the positron. So the lepton numbers are conserved. And what about charge? Well, charge incoming, we've got plus charge, nothing there, but a plus charge here. So baryon number, lepton number, and charge all conserved.